My name is Priyanshi, and I work as a software engineer at New Relic.
And my name is Sanjay, and we are part of Cloud Platforms team at New Relic.
Today, we are going to talk about something that has probably given many of you a few gray hairs: the DNS issues in large-scale Kubernetes cluster. If you have ever been paged at 3 a.m. in the morning, chances are DNS was lurking somewhere in the background. And so was the case with us. We fought this CoreDNS instability across thousands of nodes until we found a game changer: the Node Local DNS Cache. And we are excited to show you how this solution helped improve our DNS reliability. But let's conduct a quick poll. How many of you have ever struggled with DNS-related performance issues? As we expected, quite a lot of hands. OK, and how many of you are using Node Local DNS Cache? I see a few hands. Cool, let's see what Node Local DNS Cache is.
Now let's look at the agenda for this session. Firstly, we'll be looking at DNS issues in large-scale Kubernetes cluster, what is Node Local DNS Cache and its key benefits, current and proposed design for DNS in Kubernetes cluster, testing strategy, impact of Node Local DNS Cache on CoreDNS metrics, operational paranoia, lessons learned and recommendations, and finally, we have the Q&A. Now, when dealing with large-scale Kubernetes cluster, we tend to face these DNS issues. First, let's look at the CoreDNS overload. When CoreDNS is being bombarded with a high volume of DNS queries, CoreDNS might get overloaded, and this degrades the DNS performance. And next, it is noisy neighbor problem. When there is a network bandwidth contention between pods scheduled on the same node, then the DNS is negatively impacted. And let's now talk about latency spikes. We are able to see a noticeable delay impacting the overall performance of few applications. Single point of failure. Over-reliance of CoreDNS without redundancy can lead to single point of failure for DNS resolution in the Kubernetes cluster. Network timeouts. Now, during a peak load hours, the CoreDNS may not be able to resolve few DNS queries, which leads to application errors and service disruptions. Lastly, we have scalability issues. Even with horizontal scaling of CoreDNS, we tend to face these network and DNS issues, indicating a problem beyond resource allocation.
Cool. Now let's see what is Node Local DNS Cache. At its core, it's a local DNS caching agent running across each node, typically as a daemon set. Think of it as a DNS resolver running locally for your pod. Now, let's see how it works, and you can follow along with the diagram on the right. When a pod needs to resolve a DNS name, instead of sending a query to the core DNS, it first sends a query to this local caching agent. Now, if this cache has the record, it would respond back immediately. And this is where we see the dramatic performance improvements. But if this cache doesn't have the record, it would then forward the request to CoreDNS. You can follow in the diagram it as a cache miss. And eventually, we see that all the requests are processed. Now that we know what local cache is and how it works, let's see the tangible benefits it brings to the cache, to the environment. First, improved DNS resolution reliability. Local caching of DNS responses means less timeouts. So now, a pod can keep on resolving the records even if the core DNS is briefly unavailable. Second, we see reduced core DNS load. By handling repetitive queries, the cache offloads drastically, and hence it reduces the bottleneck performed by the CoreDNS. Finally, we see minimized external DNS dependency. A local cache lessens the reliance on the upstream DNS. That means lower latency and fewer external timeouts.
Now let's look at the current design for DNS in Kubernetes clusters. We have an application deployed as a pod, and this initiates a DNS lookup. And this request is sent to the local DNS resolver. Now, local DNS resolver, looking at this request, and finds that the DNS policy of this pod is cluster first. Hence, it forwards this DNS request to kubeDNS cluster IP. And kubeDNS cluster IP, once it receives this request, it gets mapped to a replica of CoreDNS. And CoreDNS checks whether the endpoint in the request is either an internal or an external endpoint. If it's an internal endpoint, it sends this DNS request to Kube API server. And also, CoreDNS being configured with the DNS policy of default, it then checks if it's an external endpoint, it forwards this request to upstream DNS resolver. Now let's look at the proposed design of DNS in Kubernetes cluster after we have implemented the Node Local DNS Cache. As usual, the application initiates a DNS lookup call. This is received by the local DNS resolver. Local DNS resolver, instead of sending this request to kubeDNS, now it sends to a specialized local linked IP of Node Local DNS Cache. And Node Local DNS Cache, receiving this request as a TCP or an UDP call, then checks whether it's a cache hit or a cache miss. If it's a cache miss, it sends this DNS request to kubeDNS cluster IP, which then forwards this request to CoreDNS. And CoreDNS, as usual, checks whether it's an internal or an external endpoint. And if it's an internal endpoint, it sends to Kube API server. If it's an external endpoint, it sends to an upstream DNS resolver. Now, if it's a cache hit, then Node Local DNS Cache resolves the DNS request within the node. This dramatically reduces the latency.
Now let's look at the testing strategy. The primary aim of this testing was to compare the DNS latency across hundreds of nodes and hundreds of clusters and thousands of nodes in New Relic. So we tested all the clusters with and without the cache, and here are the results. So this first slide shows performance testing which we did in AWS using a DNS perf test tool. Here we tested under multiple QPS or query per second scenarios, 500, 5000, and maximum QPS levels. Now let's see the table 1, AWS cluster without Node Local Cache. And you can follow along the pink column query loss percentage. If you see at 500 QPS, the query loss percentage is 0.05%, which increased to 0.08% with the increasing load, that is the maximum QPS. We also see the latency increasing with the increasing QPS levels. Now let's compare this result with the cluster with the local cache enabled. At 500 and 5000 QPS, 0% queries were lost, which is quite stark. And at maximum QPS, it was minimal 0.03%. Here, the latencies also increased with the increasing QPS, but we saw 96.92% improvements for the average latency for the maximum QPS. So as the conclusion for this testing, we found that both the latency and the DNS performance improved with the local cache in the cluster. Now, let's see the second slide for the testing, which shows the results for Azure cluster using the same DNS perf test tool. Here also, we tested under the 3 scenarios, 500, 5000, and maximum QPS levels. Now, if you see that in both the tables, query loss percentage is 0. And no, it's no magic. In New Relic, for all the Azure cluster, we use Cilium CNI under the hood. And for those who don't know, Cilium CNI is known for its high-performance DNS and networking capabilities. And so there were no packets dropped here. But still, let's compare both the tables and see what difference is this cache making. So let's follow first table. If you see, for 500 QPS, the average latency is 0.002 approximately and increased to 0.09 for maximum QPS. Now coming to table 2, which is Azure cluster with the cache, we saw the value to decrease for 500 QPS to 0.00009. Very minimal, right? And that increased at maximum QPS to 0.002. Here, we saw an overall of 96.5% improvements in latency. So, as a result, we concluded for Azure, though Cilium CNI was making sure that DNS was performing well, but the latency improved, thus optimizing the cluster further. And this is the final testing results where we tested an AWS cluster with the external load using an iPerf tool. Here also, we tested under the same scenario of the QPS levels, and we tested it for 10 minutes. Let's see the table without the local cache. And you can follow along the pink column in the table. At 500 QPS, we saw 0.3% queries lost. With the increasing QPS to maximum, we saw 0.7% queries lost. Now, if you remember the previous slide, for the AWS DNS-only testing, these values were low even without the local cache. And this is where this external load is making a difference. Now, here also we see that the latencies keep on increasing with the maximum QPS levels, and that is also higher compared to the previous results. Let's see the table 2, where the cluster is tested with the Node Local Cache and the external node. At 500 and 5000 QPS levels, we saw 0% queries lost, which is highly remarkable. And at maximum QPS, we saw a minimal 0.003% queries lost. Also, the latencies here showed a remarkable improvement where at the maximum QPS, the average latency improved by 99.3%. So a key takeaway from this testing was that even with the added external load, the AWS cluster was able to perform remarkably with the local cache enabled.
Now let's look at the impact of Node Local DNS Cache on CoreDNS metrics. We have enabled monitoring for CoreDNS using New Relic and created these New Relic dashboards. We'll be looking at two important metrics here, which is request forward duration time and request response time. Now let's first look at request forward duration metric. This is the time taken for a forwarded DNS request to receive its response from an upstream server. And on the left-hand side, we have shown the New Relic dashboard where we have shown it without the Node Local DNS Cache. On the right side, we see it with Node Local DNS Cache. The request forward duration time has an average of 30 milliseconds without the Node Local DNS Cache. And with Node Local DNS Cache, we are able to see an average of 1.5 milliseconds. This results in a 95% average performance gain in DNS. Now let's look at request response time metric. And here, this is the time elapsed for a DNS query to receive by a local cache and its response sent back to the client. Without the Node Local DNS Cache, it is an average of 15 milliseconds, while with Node Local DNS Cache, there is an average of 250 microseconds. This results in an 98.5% average performance gain, which is quite remarkable. Now let's look at something more important for system sustainability, which is operational paranoia. Operational paranoia is a proactive, and disciplined mindset for engineers to assume that systems can fail in an inconvenient and unexpected manner. It is the art of asking what if on every component, dependency, and in the system. Now let's look at two scenarios for that. First scenario is Node Local DNS Cache failure. What we basically did was we went ahead and deleted the Node Local DNS Cache daemon set to test the system resilience. Here are the results. The DNS resolution did not fail, and all the DNS requests were successfully redirected to CoreDNS, ensuring service availability. And the impacts of this test was the system performance degraded due to the absence of cache, and this test also highlighted that the system can withstand a cache's failure, but also it indicated that the cache is very important for optimal performance.
Scenario 2, CoreDNS failure. In this, we deliberately broke the CoreDNS, and as a result, we saw only the cache requests were be able to get processed. And we also saw that all the new requests that were going were not be able to process because CoreDNS was not there. So as a conclusion, we found that CoreDNS remains critical and is the source of truth for the Kubernetes environment.
Now let's look at the lessons learned here. Firstly, we have significant performance gain. Implementing the Node Local DNS Cache resulted in a 95% average improvement in request forward duration time and 98.5% average increase in request response time, drastically reducing the latency. Secondly, we have increased system reliability. The cache significantly reduced the load on CoreDNS, as well as it minimized any external dependency for DNS. This led to fewer timeouts and a stable environment. Graceful degradation. In the event of Node Local DNS cache failure, the system has been able to successfully fall back to CoreDNS, ensuring continued service availability with degraded performance. CoreDNS remains critical. While the cache handles a significantly high volume of requests, CoreDNS is the source of truth. CoreDNS failure can lead to a failure in all new uncached DNS queries.
And these are the recommendations from our end. Adopt Node Local DNS Cache as it is a highly recommended DNS practice and it improves. And you saw the metrics and the metrics don't lie. We also recommend to implement comprehensive monitoring to monitor both the Node Local Cache and the CoreDNS for the overall stability of the DNS infrastructure. That's all we have. Thank you so much. I hope you like this session. We are open to questions now.
Yes, a question.
Yeah, please. You're talking about the TTL, right? How TTL works in Node Local Cache? Yeah, so I mean, we can set the TTL in the core file. We have like denial and success where you can give the TTL. But in our case, in our clusters, we didn't set this up because we wanted the default TTL, which is set for each query, to be retained like that. I think for certain services you want it not to be cached, we have something called denial in the spec for the core file. So there what would happen that it would not query that particular domain again and again. So it's like a negative caching. But particularly if you don't want to cache a request, that's not available as of now for our information. Yes, please. Can you speak louder.
Yeah, the question here is whether external websites also we can use the Node Local DNS Cache. Yeah, obviously, like we can use it. So there is a TTL maintained for the DNS record, right? So after the TTL is over, it automatically destroys the record from the cache. If you want to manually remove it from, you can just restart the Node Local DNS Cache. Yep. He's asking how many DNS queries that we have. So here are the total queries that we have used for the DNS cache.
So if you see like the QPS levels, 500, 5,000, only 499 out of 500 were able to make through. And if you multiply this value with the 10 minutes that we tested it for, you would see that it is around 3 lakh of queries for 500 QPS. Does that answer your question?
Yes, the question here is, are we caching all the requests or is there any specific percentage? Right? Yeah, we are caching all the requests here.
So the question here is that why are we using Node Local DNS Cache as he understands that it would avoid the DNAT and IP tables rules? Why are we not installing CoreDNS pod on every node? Is that right? So in our clusters, we have like around 3 to 4 pods running across the cluster. And we wanted to do so because we don't want to overload each node with the core DNS pod. I mean, that was an option that we could have done, but that comes with its own cons, right? So we tried out something which were more efficient in that way. But yeah, we could try that out. Okay, so you wanted more resources on Node Local DNS Cache, right? Yeah, we can give it to you. We can connect and we can sort that. Yes, please. So the question is, if a record gets updated, how do we update in the Node Local Cache? So sir, for that, we have something called TTL or time to live, right? So that particular query itself, like the URL or domain, would come along with its TTL. So by default, we are not making any change in the file, but you could do so. So that after 30 seconds, refresh the whole stuff. And that would then get the updated record. Does that answer? Thanks. Yeah.
Yeah, yeah, it's the same question like which was answered. Like Node Local Cache DMN said, right? You can just delete it and just recreate it. Like it should be very fairly simple. So it won't affect the existing records, and it will just restart it from the scratch, and it will start again caching. Yes, it will start from the first. It will go to the core DNS. Yeah.
Yeah, so all the data refreshes for that particular local cache for that particular node.
Yep. answer?
So the question is, CoreDNS itself comes with the cache. Why are we not utilizing that, and why are we shifted to this solution, right? So we actually did some testing on the cache, which comes along with CoreDNS, and the amount of data that we get, the number of requests that we were getting in our clusters, it was not able to handle. So and we were getting paged a lot. So we had to handle it and find a solution which could handle that many requests. Yeah, the amount of queries were really high.
And in addition to that, like the request, right? So it can go to any of the CoreDNS pod, not specifically to the one inside the node, actually. So this will increase the latency for it.
Yeah. So you're basically asking the best practices for Node Local DNS Cache, and did we test like using that or not, right? So we followed the documentation that is available on the Kubernetes page, and they have a repo as well where they have listed down all the best practices. And if you install the package right, it would come with a core file that you could set it up, and there would be like 30 seconds for the success TTL, and for the denial also 30 seconds. So that is the default thing. But based on our architectural view, we decided that we are not going to take that as a practice. We are going to implement something without the TTL, which comes by default. So the basic thing which comes by default, we really didn't test that.
And please make sure that you test all combinations and confirm it, and then you can launch it, actually. Yeah, we are currently running it on version 1.31, so it's been pretty compatible, and we are proceeding with upgrades. We don't see anything on the community yet if there is an incompatibility between the Kubernetes versions.
So the question is, are we keeping the number of pods, core DNS pods, like before, or are we calculating it? So by nature, we have not changed the number of dual DNS pods that were running previously. Just on top of that, we have added this layer. So the core DNS pod were initially made sure that it would be able to take on the request, and we didn't change that value as of now. Does that answer?
Yeah.
Yes, please.
Oh. So the question here is, why are we not using the Istio's caching instead of the Node Local DNS Cache? Is that right? So Istio comes with variety of frameworks and variety of services, right? What we specifically needed was a DNS caching agent. And also Istio is something big to manage, and it's a big hard headache for us. So what we did was we basically had Node Local DNS Cache only, and that solves our DNS caching problem. We did not have Istio installed in all of our clusters. Yeah.
So that would come like another practice that we need to install it in all the clusters and then get the cache enabled, right? So that's like more headache. Yeah.
I think I got it. So the question here is, Node Local DNS Cache can be a single point of failure. Is that right? No, actually, that's how the operational paranoia testing was done. And we made sure that we deleted the Node Local DNS Cache daemon set just suddenly, and the DNS resolution still did not fail. So it's fallback to CoreDNS, basically. And we saw that the DNS performance degraded, but still the DNS resolution happened.
He's asking for the specification that has been added for it to fall back on CoreDNS.
By default, it works like that. Yeah. So the question here is like, how are we monitoring the Node Local DNS Cache, right? So we do have few metrics which Node Local DNS Cache also exposes, since it's a wrapper on top of CoreDNS, right? They both have more or less the same metrics. So however we are monitoring the CoreDNS, same way we can monitor the Node Local DNS Cache. Is that right?
We are up with time. Any more questions? Yeah, we can take the last question. Oh, he's asking what is the request forward duration metric.
Can you once again repeat it?
Oh, for the pod, what's the
For the container is asking.
you're asking what's the limits that we have set for the pod container, right? For the node local cache.
Currently, we haven't gone with any particular limit. We have
We have actually set the by default YAML that comes with it. So we haven't set any request that it would need. I don't think that's a major thing that limits memory or the CPU that it would request. We can actually discuss this further offline. We'll just wrap it up now. We're close to the time. Thank you so much, guys, for joining.
Thank you.